So I'm going to talk about recent work on the unified parameterization. So title of this talk will be Unified Representation of Deep Moist Convection in a atmospheric model. So here we focus mostly on the deep convection, and we are focusing on when the resolution changes, how do we adapt the parameterization. The background of this idea is that as far as the representation of deep convection is concerned, we only have two kinds of moist parameterizations. The first one is so-called highly parameterized, as known as the cumulus parameterization. And the other one is used in a very high resolution model, such as the cloud resolution model. So it's called explicit simulated. So we treat the microphysics explicitly. And hence, we have two families of the atmospheric models, separate from the horizontal resolution, as in the x-axis here, and the degree of parameterization here. You notice that the GCMs generally have a lower resolution and use highly parameterized moist convection. But in a cloud resolving model, deep moist convection is actually explicitly simulated. Due to the computation increase in the recent years, most people try to increase the horizontal resolution of general circulation models. This is done in a very brute force way by just changing the horizontal resolution. But the results are actually not very satisfying because changing of the resolution requires tuning. Tuning makes the model not generally better. So this part actually we got hampered by this actually cumulus parameterization problems. More than that, the problem of this increased resolution is not limited to the convergence problem. It's actually a problem that we need to have a model that as the resolution increases, such as here from the 100 kilometer to the cloud resolving resolutions, in that the transition is actually very smooth, such as the arrow drawn here. So the GCM should converge to a physically meaningful system, such as a global cloud resolving model. To develop parameterization for such kind of application, it's actually we have to go back to the root of the assumption of the cumulus parameterization. So here we look back to this simple assumption actually used in most models, is that most parameterization schemes assume that the fraction area covered by the convective cloud is actually very small. This is reasonable if you think the grid size is pretty large. For here, you're looking at something few hundred kilometer grid cell inside the GCM. So you expect that the cloud area, deep convection, actually occupy only a very small fraction. So the parameterization work is actually on the environment. So the work produced by the cumulus parameterization is the temperature and water vapor predicted by for the cloud environment. But you think if you have the very powerful computer and you increase the resolution to a cloud resolving scale, such as the right-hand side of this figure, you notice that in that grid cell, if the cloud occupies the whole grid, you don't actually have the environment. So this causes a serious problem. So in that sense, the simple approach to open this unified parameterization is to eliminate the assumption of this small cloud fraction here. Here, we didn't actually run a general circulation model to do this work. Instead, we use a high-resolution cloud resolving model to test our hypothesis. The dynamics are developed by the Chien-Ming Wu 2008 and the Wooden 2010. The microphysics use a very simple Bach microphysics developed by Cougar. So here we have a horizontal resolution of horizontal grid size of 512 kilometer and resolution of 2 kilometer. And we choose two types of typical tropical convection, such as the one with shear score line-like convection, and the other one with the background shear is the popcorn type convection. Here we are looking at the domain slice of the vertical velocity here. And the analysis approach is to slice this the big grid, 512 kilometer grid, into small subdomains. And we treat these small subdomains as a GCM grid size. So in that case, we have statistics based on the full domain size 512 kilometer down to the cloud resolving 2 kilometer grid size. In that case, we have we can see the convective contribution to this the large scale in the various horizontal resolution. So here we define the fraction number of grid points with vertical velocity greater than 0.5 meter per second inside a subdomain, and we average only the cloud containing subdomains here. So, for example, in this panel, we have the averaging subdomain size from the 512, which is the whole domain, down to the 2 kilometer, which is the cloud resolving subdomains. So you can see a very sharp contrast here is that when the resolution is small, when the resolution horizontal grid size is large, such as the left-hand side here, the cloud fraction is actually very small. But it picks up its accelerating rate when the resolution increases, such as here, around 32 kilometer. This is for the shear case. The same goes with a non-shear case, the popcorn type convection. So the convection actually pick up slightly later, 32 to 16 kilometer. So we know that from this simple analysis on the cloud fraction, we know that the assumption of the small sigma is valid only for low resolution. Here we mentioned that this low resolution is actually, say, larger than 32 to 64 kilometer. So the work of this unified parameterization is in this range, from 32 to 2 kilometer range. Because in that side, larger than 32 kilometer, this assumption actually still work in the GCM. So the goal of the unified parameterization is the unification of model physics of GCM and CIM through generalizing the conventional cumulus parameterization. This talk is slightly different from our previous one, is that we know the actual rationale of this, why this unified parameterization work based on this this analysis. So previously we think this is actually this is called convergence thing, because we have cloud occupying only a small fraction and occupying a whole grid. So in this two end, the parameterization have to converge at this two end. But we don't know why this is distributed in the middle of the resolution. So this time we try to use a simple approach to use the top hat profile to analyze our results. So this is actually the assumption used in all conventional parameterizations. Here we are looking at a plot slightly different from our previous one, because we changed the rationale from the horizontal grid size to this area covered by the convex clouds. So we think that this problem is not limited to just the changing of the resolution. It's actually changing of the fractional convective cloudness. So I'm going to explain how we come up to this figure later. But first, you have to notice that the total transport of this eddy transport, total transport is by the WH. The whole transport by the model is drawn by this red line. So this is all the convective activities contributed by the clouds. And the green and the blue line are actually the eddy transport. So this is the subgrid scale process transport by this in this model. So here we discuss some notation of this analysis. We know that the C means the cloud value, and the big delta here is the cloud environment difference. This is actually very important in our later discussion. So the bar means that the sigma multiplied by the C sub C and 1 minus of the environment. So this is the average means the cloudy part average and plus the environment average. So based on that, we have our vertical velocity separate as this form, the environment plus the cloud part. So by that notation, we have our eddy transport, the double prong 5 prong here, The phi can be any thermodynamic variable. Here we can think of it as more static energy. So it can be written in this form. It's a sigma y minus sigma, the cloud environment, the product of the cloud environment difference plus this term. Now the difference from the conventional parameterization and the unified parameterization is that in the conventional parameterization, we assume that the cloud environment difference is actually small. So we assume that sigma equals 0, as is closer to 0. So we use a mass flux approach to parameterize this eddy transport. So we know that the vertical velocity and the cloud fraction is a product as a one variable here. But in the unified parameterization, the sigma is not small, so we retain the sigma here. So the eddy flux, the form, it looks like a sigma, y minus sigma, with this cloud environment difference product. So the main difference of the unified parameterization and the conventional parameterization is that we retain this sigma dependence in the formulation of the eddy transport. So here we want to show that this is actually true. So we want to show that if this cloud environment product is independent of sigma, then the eddy transport has the sigma dependence as shown previously. So you can imagine that this is actually the cloud environment difference of the vertical velocity. So you can think of cloud has the same vertical velocity and the environment has the same similar vertical velocity. And here you see that this the cloudy area has the same more static energy, and the environment has the same one. So the product represents the cloud environment difference, and it's physically it should be independent of this the cloud fraction. So we calculate that and show that they actually did. So this is the sigma of our shear case, and this is the number shows this cloud environment product of delta W delta H. You see that this number is actually independent of the sigma. So the product of the cloud environment difference shows actually the convection strength. So this is not saying that the fractal area covered by the convective clouds. So if we know that, the unified parameterization has now been more clear to us, because it's actually the eddy transport of the subcritical processes actually depend on the sigma 1 minus sigma, this term here. So we know that if this is independent of the sigma, the eddy transport depends on the sigma through this term here. And this is very different from our previous explanation, saying that this is just a simple choice of convergence. So this is our target, assuming that cloud environment are homogeneous independently. So the eddy transport is the blue line here, and the total transport is the red line here. And here we fit this dot line here, shows the sigma dependence here. So this dependence it's not limited to this resolution. It's actually similar in other, say here is the 16 kilometer resolution or a 32 kilometer. But notice that in the lower resolution, we don't usually get very high convection cloud in here. So we only have a small fraction here. But the situation might change if we've changed the convective systems. So here we show that the sigma dependence of eddy transport is similar between different resolutions, and the value of sigma, which I didn't show, of the product here is also similar. The next thing I'd like to discuss a little bit about is the parameterization of uncertainty here. Because we previously think about the convection has a lot of randomness or a lot of its own variability. So we think that the parameterization of these subcritical processes should have a large variability too. But here we are looking at the similar plot with the grid scale total transport here. So you see that as the resolution gets higher and higher, the variability gets larger and larger. But for the subgrid part of this transport, the eddy transport, we need to parameterize. is actually getting smaller, because in that, to the end of the high resolution, 2 kilometer resolution, all the transport is taken care by the grid scale. So the eddy transport you need to primarize is actually very small here. So this shows that it is important to distinguish the fluctuation of the total transport from the uncertainty of the primarization. The green line is the transport we need to primarize. The red line is the variability generated by the grid scale convection. So here's a summary of the uncertain part. So we know that back in the Arca-Schubert 1974, we know that we need to consider horizontal area, which is large enough. This large enough thing hasn't been a clear definition until recently. So we need to know this area has the ensemble of clouds. So the uncertainties comes from, in the standard conventional view, is that the small sampling size. But here we show that the uncertainty actually depends on the variance as well as the sample size. The other studies show that the population itself can restrict the ability of establishing an equilibrium, meaning that the cloud system can change the equilibrium state. But here we show that ability also depends on the efficiency. There's a delta W delta H product in the eddy transport by the individual clouds. Okay, so I'll end here. Question?
Yeah, it's a very interesting argument, actually, on the scale thing. You know, you kind of show me on one slide, so probably philosophically, I understand you're trying to argue the global GCL will converge to global CIF. But I'm not sure if you know, some other people like Adrian Tuck and Tim Palmer will agree with you. So there has been recent topics on this. There's a scale branch, because if you look at the energy spectrum, there's a clearly dominant by two different modes of transition scale. So people would argue if you have one scale dependent scale to predict whether you can really cover the other things. Physically speaking, that makes a lot of sense. That's why I understand why, when Arca-Schubert, they set the so-called large domain, that's how to make that safe, because you're trying to not cross border, rather than second-hand gassing the residuals in that so-called subgrid scale. But when you reach the scale, you can resolve both energy spectrum. Then it's hard to say. I guess probably this is a more philosophical debate on that. So I don't know what's your take. You want to draw a line there? So yeah.
I can answer this shortly, because the connection between the large scale and small scale spectrum is actually the mesoscale. So this is sort of breaching this mesoscale thing in our primarization. So in a grid scale, that's like a 20 kilometer, not small enough to resolve the convection, but it's not large enough to contain all the convective clouds in the grid scale as shown in these slides. In this point, you need the primarization that doesn't overdo its job. That's our main goal of this primarization. So based on this formulation, the eddy transport is relaxed by this convective cloud fraction.
Yeah, so sorry to follow that eddy part. Actually, you were talking about a not real eddy rather than the
subgrid.
Yeah,
subgrid. So that the definition of the subgrid primarization change.
Not a 503 parallel.
Yeah.
So that's different than what
The primarization need to be used in the model, changes definition from the GCN to the cloud resolving model.
It is a very interesting argument.
So have you considered the cloud top height?
Well,
For the first part, the cloud top height, there's if it is a very high or very low for the thick convection when you do the sampling. not sigma.
So far, I have checked the whole levels, like from surface to 15 kilometer. The dependence doesn't change very much based on this eddy transport idea.
So do you suggest that larger than 30 kilometers is fine for parameterization?
Sort of, based on the sigma dependence analysis.
I have a question which has to do with the subsidence portion.
Mm-hmm.
The convection scheme would not trigger, and yet you would have, in the original concept, the subsidence in the large scale.
Mm-hmm.
Now your subsidence, how much of that contribution to the total grid flux?
Most of the convective induce the substance actually near the cloud edge, right? But
near the cloud edge, or does it? Because it could be in more than one grid.
yeah, it can be large scale. Yeah, but the key idea is that we only take care of the subgrid part.
But you have the high resolution data.
Yeah.
Ask yourself, how much of the subgrid scale transport by the subsidence you're ignoring?
Yeah.
If you don't,
And the good news of this unified parameter is that as the resolution is very high, the grid scale take care of much things.
But it's in between that you need to know, do I need to worry about multi-grid point parameterization or not?
Okay. So that's conclude this section, and we have a 20-minute break.